Peut-être qu'il y a déjà un lien qui est connecté pour le faire. Ça ne va pas encore. Ah, ok. Donc,
Prova, prova.
Hello.
Salut Giovanni,
Salut, tu m'entends bien?
je t'entends très bien et je crois que c'est la même chose pour toi.
Ouais. Et Giuseppe, je ne sais pas si... euh, Bon, du coup, je pense que c'est bon pour toi,
Ouais,
Nathalie.
c'est bon, super.
Et...
Ouais, écoute, je vais couper ma vidéo et puis
Oui, oui, ok. Giuseppe, mi senti? Can you hear me?
Sì,
Ok,
ciao.
ciao. Va bene, allora. Mi sembra che va tutto bene. Perfetto.
Ecco. Non mi vedo, ma
Non ti vedi, dici?
no, tu mi vedi?
Io sì, ti vedo bene. Sì, sì.
Ah, bene, perfetto.
Allora, aspettiamo.
Ecco. Quindi iniziamo tra un quarto d'ora?
Sì, tra 10 minuti all'una.
Va bene.
Aspettiamo che arrivino tutti e poi cominciamo.
Per capire dopo la tua presentazione, quindi ci sono le domande.
Sì, e dopo, come dicevo, sì, nel messaggio c'è la deliberazione, dovreste aver ricevuto un link separato.
Sì?
E poi c'è un momento insomma, in cui si conferisce il titolo, diciamo. E poi è finita.
Va bene.
La deliberazione non so bene quanto duri, ma penso che dipenderà da... Sì, un po' aleatorio. La mia presentazione sarà tra 45 e 50 minuti.
Va bene. Ok. Quindi tra 10 minuti.
Sì, sì, se vuoi riconnetterti tra 10 minuti non c'è.
Sì, ok, perfetto, a dopo.
Grazie, a dopo. Hello. Hello, Annabella. Can you hear me? Can you hear me, Annabella?
Ah, bonjour, ça va, j'avais pas le son.
Ok.
Ça va?
Oui, ça va, merci. Ça va, merci d'être là.
Oh, je t'en prie. Ben, je suis la première alors.
Non, il y a Nathalie qui s'est connectée.
Ah oui, d'accord. Je ne voyais pas.
Bonjour François. Bonjour.
Bonjour.
Bonjour Giovanni.
Ah.
Bonjour. Tu m'entends bien?
Oui, très bien. Et toi?
Oui, donc je suis dans les locaux du CEMAP.
Oui, je sais. Très bien. Et donc, François, tu es avec Thierry, peut-être?
Je ne suis pas dans la même pièce que Thierry, mais Thierry est à côté dans son bureau et je suis dans une pièce juste à côté. Mais on a jugé que c'était plus facile qu'on ne soit pas dans le même bureau.
Oui, ok, effectivement. Donc, il manque encore Yann. Bonjour Arnaud, tu m'entends bien?
Ouais, j'entends bien. Et toi?
Oui, très bien.
Si?
Giovanni, j'ai besoin de savoir, c'est en anglais ou en français?
Non, en anglais. La présentation, c'est en anglais.
D'accord, tout est en anglais. Et les membres du jury, il y a des non francophones, hein?
Oui.
D'accord, c'est important.
Ouais, Giuseppe, il doit pas parler, enfin, il parle pas très bien français.
Ouais. Et en plus, je ne sais pas si Yann n'est pas en français, je ne sais pas.
D'accord.
Dès qu'il arrive, on peut lui demander, mais de toute façon, il n'est pas
Non, mais
français.
c'est pour savoir.
Je tiens juste à dire que j'ai pas reçu ma bouteille de champagne, hein.
Arrête, ça va.
Tu monnaies ta participation à des jurys de thèse et d'HDR.
Non, mais normalement, on l'a après. Là, c'était pour fêter à la fin, tu vois, d'avoir qu'on puisse tous être un petit peu festifs quand même.
Toi, tu es festif.
Thierry a quelques problèmes de connexion. J'arrive, hein. Je vais régler ça. Yann là. Allô? Thierry est là. Yann, can you hear me?
Yes, I hear you. Hi.
Okay, hi. Thank you. Thank you very much for coming.
Hi.
Okay, I guess everybody's here. No.
Pardon. Désolé. Mea culpa.
So I could start whenever.
Yeah, I think that we must agree on the president of the committee, Thierry.
Yes, and I would suggest that François would be a perfect president if he agrees and if we all agree with that.
And for sure,
Perfect.
I agree with pleasure. Thank you.
Okay, so
Yes.
thanks. Okay, so I'll let you, François.
Okay, so thank you. So Giovanni, so you have around 45 or 50 minutes for your presentation.
Okay. Thank you very much, and thank you all for being here, especially the members of the jury and the referees. So I would like to start this presentation about some of the results I've obtained over the last 4 or 5 years by giving some background on a mathematical problem that I have studied quite intensively, and this is the Schrödinger problem. So it all starts with a simple thought experiment that was proposed by Schrödinger a long while ago. So his question was the following one: suppose that you observe a system of particles that are diffusing, and that you take a snapshot of the system at 2 consequent times, time 0 and time capital T. The question was, conditionally on this information, what was the most likely evolution of your particle system? So nowadays, thanks to large deviations theory, we can formulate this question as the question of minimizing the large deviation rate function associated to the particle system under marginal constraints, representing the observation that you have made at time 0 and at time capital T. So in order to start writing down a couple of formulas, let me consider probably the simplest particle system one could think of, namely independent Brownian motions. Then in this case, the large deviation rate function is given by Sano's theorem, and it's the relative entropy. And therefore, the corresponding problem is that of minimizing among all path probability measures, was marginal at time 0 is mu, and was marginal at time 0 is nu. So mu and nu represent the observed configurations. And what you minimize is relative entropy of P against a reference measure R, and R is the law of the Brownian motion started at mu. So this dynamic problem, in which you have a time variable, has a static counterpart in which you minimize relative entropy, now against the joint law of the Brownian motion at times 0t, and you minimize over all couplings of the given marginals mu and nu. So here you start saying that there is a certain analogy between the Schrödinger problem and the optimal transfer problem, and I will develop on this analogy throughout the whole presentation. And the passage from the dynamic to the static formulation is achieved by mixing up the optimal solution of the static formulation with Brownian bridges, pretty much like what happens in optimal transport, where you lift static solution to dynamic solution with geodesics. Okay. I would like to mention that there are 2 other alternative formulations of this Schrödinger problem. There is a stochastic control formulation that stems from the observation that a probability with finite entropy against the Brownian motion is essentially Brownian motion plus a drift. In this stochastic control formulation, you have the right to control a Brownian motion through a drift field, alpha t, in such a way that you end up at the target configuration mu, and you do so minimizing the overall control effort. So once you pass from the stochastic processes level to the PDE level, then you transform the stochastic control formulation into a fluid dynamic formulation. in which you do exactly the same thing as before, the only difference being that instead of controlling the Brownian motion, what you control is the Fokker-Planck equation. And the passage from the stochastic control to the fluid dynamic is made by taking the marginal flow for a path measure admissible for the stochastic control problem and realize that it is indeed an admissible flow for the fluid dynamic formulation. Okay, so far I've just discussed instances of the Schrödinger problem where the particle system at the beginning was made of interacting particles. But of course, if you go back to Schrödinger's idea, nobody tells you a priori that particles were IID. So it makes sense to consider Schrödinger problems for truly interacting particle systems. So here I put an example. So the n particle system here is taken to be the approximation of the Mekin-Vlasov dynamics for a certain interaction potential W. So particles now interact through the drift, and the interaction is of mean field type. The large deviation rate function for this problem is known due to Dawson and Gertner, and it leads to the following entropic formulation. So it looks pretty much like the classical problem. So you minimize over the same set of path probability measures, but now instead of minimizing against the fixed reference probability measure R, you minimize relative entropy of P against a probability measure that depends on P itself. So this is the mean field part coming in. And how you cook up the gamma of P once you have P? Well, you first consider the marginal flow of your path measure P. Then you convolve the marginal flow with the gradient of the interaction potential. This gives you a drift field. And then you solve for the SDE Z, whose drift field is given by the convolution of the gradient of the potential with the marginal flow, and the diffusion matrix is 1. Okay, so this is one example of a Schrödinger problem for an interacting particle system. But what you should probably keep in mind is that as soon as you have a particle system for which you're able to compute dynamic velar deviations, then you have a Schrödinger problem that is worth studying. Okay. So now that that we know what the problem looks like, I would like to discuss a couple of contributions concerning optimality conditions for the various formulation of the Schrödinger problem we have seen so far. The first contribution is about optimality conditions for the problem written in fluid dynamic formulation. And in order to present the result that you will see in the next slide, I would like to give some background on certain geometric constructions associated to optimal transport. Namely, I would like to discuss a little bit the so-called autometric, that is just a way to turn the space of probability measures over a given Riemannian manifold into a huge infinite dimensional Riemannian manifold. In a nutshell, the construction is as follows. You first consider a point in your big manifold, which is a probability measure, say mu, and then you declare that the tangent space at mu is given by the closure in L2 of the space of gradient vector fields. Then once you have identified the tangent space, you can define the Riemannian metric on the tangent space, and you do so saying that the scalar product between the vectors, which are two gradient vector fields, is given by their L2 mu inner product. And the surprising thing is that this formal Riemannian construction actually is compatible with optimal transport. So what do I mean by this? I mean that if you take the geodesics that are produced by this Riemannian metric, then they coincide with the geodesics of optimal transport. And more than that, this autometric allows for explicit calculations. Most importantly, if you have a regular enough curve, which I denote by mu t, then you can compute its speed that I denote by vt, and it's the only solution of the continuity equation associated with mu t, such that vt belongs to the tangent space at any point in time. You can go one level further. You can even compute the acceleration of a given curve. So the acceleration, since we are on a Riemannian manifold, is a covariant derivative of the velocity along the curve itself. And it turns out that it's the following vector field. So you first take a time derivative of the velocity field, and then you take 1/2 the gradient of the square norm of the velocity field. Okay, now that you have all these beautiful constructions at hand, you can wonder what is the equation satisfied by an entropic interpolation in this Riemannian structure. So here I take as a reference dynamics for the Schrödinger problem, a Kolmogorov diffusion. So I have my Brownian motion, I add the gradient drift, and now my particles live on a Riemannian manifold rather than on RD. And I denote by bold M the invariant measure for my Kolmogorov diffusion. And the result is, as soon as you have some regularity assumptions, then the entropic interpolation, that is the optimal flow for the fluid dynamic formulation of the Schrödinger problem, rewrites as the following equation: acceleration equal to 1/8 times the gradient of a functional I, and the functional I is the Fisher information. So this equation is a Newton's law. So it's just the transposition to this complicated Riemannian manifold of the very simple equation on RT, x dot dot equal minus gradient of I computed at x. And this equation allows to give a possible answer to a long-standing question, which is, what is the second order equation that best describes a Brownian bridge? So this question has been around for quite a while, and there are already several available answers. So the one I'm proposing here has a couple of interesting features. The first one is that the acceleration that we consider is Riemannian, and therefore you can do with it all types of manipulations that you would do with the standard acceleration on RD. And the second thing is that the right-hand side, so the acceleration field, has a very clear and full interpretation as the gradient of a function that we know very well. It is the Fisher information. And the Fisher information, having the interpretation of the gradient of the entropy, has a lot of useful property that I will use eventually in the next slides to derive fine properties of entropic interpolations. Okay. I would like to move on to present a second set of optimality conditions. So now we change the perspective. We move from the geometric setup to the probabilistic setup, and we move from the classical Schrödinger problem to the mean field Schrödinger problem. So here we write optimality conditions in the form of a forward-backward stochastic differential equation of Mikin-Vlasov type. So the result is as follows: under certain regularity assumptions on your interaction potential W, then if you denote by X the canonical process under P, where P is taken to be an optimizer of your mean field Schrödinger problem, then the triplet X, Y, and Z is a solution of a certain forward-backward stochastic differential equation. Let me just give you the interpretation. So the first equation is giving us the dynamics of the canonical process, and it is telling us that the canonical process is the Mikin-Vlasov dynamics for W plus a correction, which is the Y process. And then the second equation, the adjoint equation, is giving us the dynamics of the correction. And the dynamics of the correction has two parts. There is first an absolutely continuous part where you see the role of the Hessian of the interaction potential coming in. And then there is a second part, which is the martingale part. Okay. So to sum it up, we have seen that there are two very, very different angles under which you could consider and write down optimality conditions for the Schrödinger problem. And in the next slide, I would like to propose a kind of unified view of these two approaches. And in order to do so, I would like to take one step back and recall certain relations between stochastic processes and evolution equations in the space of probability measures. So there's a beautiful result by Otto and co-authors that tells that if you take the simplest possible stochastic differential equation of first order, so this one, then this equation provides you with a pathwise representation of a gradient flow in the space of probability methods. So the gradient flow is this equation here, and it's just the equation velocity, so x dot, if you want to think of it in RD, equal to minus the gradient of some functional, and the functional, in the case of the Brownian motion, turns out to be the relative entropy. So this is what happened at first order. And the calculations that I've outlined before tell you that this nice correspondence is also preserved at second order. So if you consider the second order counterpart to the gradient flow, then what you get is exactly a Newton's law, so acceleration equal to the gradient of something. And actually, if you want to be more precise, in order to get this equation here from the equation on top, you just take derivative on both sides here, and you will see that by taking derivative on both sides here, you end up exactly with acceleration equal to the gradient of Fisher information. And the nice thing is that this second order equation in the space of probability measure admits as variational representation a pathwise stochastic differential equation. And this pathwise stochastic differential equation is now a forward-backward stochastic differential equation. So if you want to sum it up with a single sentence, what you could say is that it is more or less the same thing to say that the marginal flow accelerates like the gradient of the Fisher information, and to say that the drift of a diffusion process is a martingale. So you will see that between Fisher information and martingale, there is a tight relation. Okay, this is as much as I wanted to say about optimality conditions. So now let's move on to the analysis of the behavior of optimal curves. In particular, I would like to discuss the relation with the so-called turnpike property in control. So what is this turnpike property? In deterministic control, it is the general belief that optimal trajectories of a dynamic control problem tend to spend most of their time in close neighborhood of certain steady states that are called turnpikes. The turnpike is a synonym for highway. If you want to be a bit more precise, the sketch of the dynamics should be as follows. So you first observe a fast transition from your initial state to a neighborhood of the turnpike. Then you stay for a long time around the turnpike, so you have a long, slow phase. And then you observe a fast transition from the turnpike to reach the final state. And if you think at Schrodinger's thought experiment, the turnpike picture fits quite well with it. And let me explain why. Suppose now that the blue pictures are the two observed configurations at time little t equal to 0 and little t equal to capital T. And suppose now that somebody asks the question, okay, now you have observed those two pictures, tell me what the picture and time little t equal capital T over 2 should look like. And of course, if you know that your particle system is sufficiently ergodic and the time interval between the two observations is sufficiently large, what you believe is that in between t and t over 2 and between 0 and t over 2, the particle system has enough time to mix. And therefore, even if those two pictures don't look pretty much like the invariant distribution, the picture in between should still look like the invariant distribution. And the question we have been trying to address for a while is how to turn this into a rigorous mathematical statement. And here is an example of what you could do. So we look for an assumption that guarantees ergodicity for our particle system. So here I'm still in the framework of the classical Schrodinger problem. My reference measure is a Kolmogorov diffusion. And a classical assumption that ensures lots of ergodicity for the underlying particle system is the Bakry-Amri curvature condition. So at any point on your manifold, you assume that the Ricci curvature at the point plus 2 times the Hessian of your potential is bounded below by a positive constant kappa. So if this is true, what you can show is that if you take any two marginals, mu and nu, and if you take the entropic interpolation joining them, Then if you measure the entropy of the entropic interpolation at any time against the invariant measure of the Kolmogorov diffusion that plays the role of the turnpike here, then this relative entropy is bounded above by the product of two terms. You have a first term that just accounts for the entropy of the marginals. And then you have two exponential terms, a forward term and a backward term. So if you take this term for little t equal, for instance, to capital T over 2, you will see that they are both of the order exponential of minus k capital T. And this is telling you that the relative entropy at time capital T over 2 is exponentially small. And therefore, your interpolation is exponentially close to the turnpike. And this result has the nice feature that it shows at the same time the interest of working with curvature and of working with Brownian motion for the turnpike phenomenon. What do I mean by this? Okay, the first thing which is kind of obvious is that you see here that Ricci curvature plays a role for the turnpike phenomenon. This seems to not have been noticed before. But the reason why you see the Ricci curvature playing a role is exactly because we are considering a stochastic control problem and not a deterministic control problem. So if I were to remove the Brownian motion from the Schrödinger problem, I would end up with optimal transport. And there is no reason to expect that geodesics of optimal transport do satisfy the turnpike property. Another observation that you could make is that this kind of exponential turnpike estimates actually hold in a more general framework than the classical Schrödinger problem. Actually, we have checked that they hold for a kinetic version of the Schrödinger problem and also for the mean field Schrödinger problem. And there are nice heuristics that tell you that actually they should hold in a far more general context. Okay, so I would like to conclude this section about the turnpike property by giving a couple of perspectives on possible future research. So the observation is that probabilists by now, they have developed an incredible amount of techniques in order to study the long time behavior of uncontrolled Markov processes. And at the same time, people in control, they know very well how to prove turnpike theorem for deterministic control problem. But if you look, the literature about the turnpike property for stochastic control problem seems to be much less developed. And I think it would be very nice to advance in this direction. And a possible way of doing this would be to divide the study into two phases. So first you try with a geometric approach, pretty much like the one I have outlined before. And through this geometric approach, you try to find recurrent geometric structures in control problems. So you do kind of a screening of the different control problems and divide them into categories. For instance, this structure of the Schrödinger problem is one of these possible structures, but there are many more out there that need to be found. Then typically, once you have identified the typical structures, under pointwise assumptions like Bakri-Emry, you can obtain very precise turnpike estimates. And then in a second phase, you would like to move away from this pointwise assumption and consider some kind of averaged assumptions. And in this case, the geometric viewpoint will lose a lot of its power because it's not so stable with respect to perturbation. And then what seems reasonable is to resort to probabilistic methods. So here, just to give a taste of what could happen is let's have a look once again at the classical Schrödinger problem on RD, so the simplest setting. If the potential U is strongly convex, we have seen you have all the turnpike estimates you want, but now suppose that it's not strongly convex, but it's only convex on average, like it is the case here. Then what it seems is that replacing the Bakri-Emry calculations with coupling by reflection techniques, you can still obtain turnpike estimates under this weaker assumptions. So in conclusion, I think it would be very nice to continue along this direction. Okay, now let me switch topic a little bit. Let me discuss the relation between the entropic transportation cost and various functional inequalities. Let me begin by giving a bit of background. So the entropic transportation cost is nothing but the optimal value in the Schrödinger problem. And it has been known for a while now that the Schrödinger problem converges in the short time limit towards optimal transportation. As a consequence of this general fact, you have that if you rescale the entropic cost by t and you let t to 0, then you get back the square Wasserstein distance. Actually, you can be more precise in the analysis. You can even compute the first order term in the asymptotic. So if you rescale the entropic cost by t, then okay, you have at order 0 square Wasserstein distance, and then at order 1, you obtain the sum of the marginal entropy. So the first order term is the sum of the marginal entropies. And this reveals a nice connection with the JQO or de Giorgi scheme, because you see that the function that you have here, if you freeze the nu and you look at it as a function of mu, looks pretty much like the function that you minimize in the de Giorgi scheme. So together with Luca, we tried to push this a bit further, and actually we managed under certain regularity assumption to compute the second order term in the expansion. And it turns out that the second order term is given by the average of the Fisher information along the Wasserstein geodesics connecting mu and nu. So actually, maybe here I want to say that there are two results. The second result is the one I've just told you, the exact form of the second order term. But also what is interesting is that there is a second order term. Because, for instance, if you consider discrete analogous to the Schrödinger problem, sometimes you don't even have a second order term. Okay, now let's talk a little bit about functional inequalities. So the reason why I want to do this, because now that we have seen that the entropic cost is kind of a proxy for the Wasserstein distance, you are tempted to see whether or not you can replace the Wasserstein distance by the entropic cost in some of the most well-known functional inequalities. So here I just report two super classical statements. Here is Talagrand inequality. So a measure M satisfies Talagrand inequality if and only if square Wasserstein distance from M is bounded above by a constant times relative entropy. And a measure M will satisfy the logarithmic Sobolev inequality if and only if relative entropy from M is bounded above by a constant times the Fisher information. So both inequalities are known to be implied by a curvature condition such as Bakry-Emery. And one of the things that you could observe is that actually you can obtain an analogous of Talagrand inequality by replacing W2 square with the entropic transportation cost. So under a curvature condition, you have that the cost of transporting through Schrödinger any probability measure mu onto the reference, the invariant measure M, is bounded above by a constant that is different than the one that you have here. But this is as expected because the entropic cost is bigger than the Wasserstein distance times the relative entropy function. Actually, here I said that you need the Bakry-Emery condition, but in truth, you can show that you need less than this. And let me be clear about this in the next slide. Actually, we showed with Luigia that for the entropic Talagrand inequality, you have an analogous to the famous Otto-Villani theorem, namely, as soon as this logarithmic Sobolev inequality holds, the entropic Talagrand holds. And in turn, as soon as the entropic Talagrand holds, Talagrand, the classical Talagrand, also holds with a constant that may be different from K. Moreover, this inequality has a couple of other nice features. So it is equivalent to a certain form of reverse hypercontractivity for the semigroup generated by your Kolmogorov diffusion. It is equivalent to a kind of twisted dimension-free concentration of measure property. It tensorizes, and moreover, it is valid also in a larger context, for instance, in the case of the mean field Schrödinger problem. Okay. So let me now turn the page a little bit and move to a different but still related topic. I would like to discuss a little bit some recent results that I obtained in collaboration with Richard Kraj and Daniela Tonon about the uniqueness for certain Hamilton-Jacobi equation related to control gradient flows problem. So let me present the problem at hand. So it is a control problem. What are we controlling? We are controlling a partial differential equation through a control, which is alpha t. So if I take out the control, the partial differential equation that remains admits the interpretation of a Wasserstein gradient flow with respect for the energy functional calligraphic E. So that's why here I put the derivative in Wasserstein space and not the usual gradient. So just to give an example, if E is relative entropy, then this PD is just the Fokker-Planck equation. And you have an initial starting point, which is mu, and your objective is to minimize an average cost that is made of the sum of two contributions. So you have the cost of controlling plus a running cost. You call the optimal value f of mu, and of course f of mu is a candidate solution for an Hamilton-Jacobi equation. So why would you come to the study of this problem? There are different possibilities. So the one that was my driving motivation is that you will end up studying this problem, actually a related one, but very close to this one, if you're interested in obtaining Morse-Kantorovich duality results for the mean-field Schrödinger problem. You could study this one just if you're interested in Mekin-Vlasov control, because after all, this problem here is just a fluidodynamic representation of a certain class of Mekin-Vlasov control problems. But you may also arrive to this problem if you're interested in advancing the methods for proving large deviations for interacting particle systems that have been developed for 20 years almost by now by Feng, Kurz, and their co-authors. Okay, let's now have a look at the equation. So at the formal level, the Hamilton-Jacobi equation that you can get just by a sketchy application of the dynamic programming principle is the following. So F minus the Hamiltonian equal to the running cost, and the Hamiltonian has two terms. You have the square norm taken on the tangent space of the gradient of F minus the inner product between the gradient of F and the gradient of your energy functional. So if you want to start wondering about uniqueness, you first should have a solid notion of solutions. And here, on top of the usual array of problems that you have with infinite dimensional Hamilton-Jacobi equation, there is an additional problem, is that the gradient of the energy is not really something that you can define. So the Hamiltonian is ill-defined, even if the function f was the most regular you could think of. Simply because for instance, the gradient of the entropy function is not even continuous, so there is no hope that you can define a gradient in general. So how to do? So we adopted a general idea, which is that one of abandoning the chance to working directly with the Hamiltonian H, but to try to construct upper and lower bounds, H DAG and H double DAG, with the hope that they are tight enough so that there is still a unique viscosity subsolution for the upper bound, a unique viscosity super solution for the lower bound. And I would just like to tell you a little bit how to construct these bounds. And I will do so by playing along with the analogy between this Hamiltonian and the toy Hamiltonian that you get on RD by removing any reference to the complicated Wasserstein space in the inner product and in the gradients. So let's see how to bound the action of the Hamiltonian. We take a test function. So here I take the distance square object on RD, so distance square from y. And why do I restrict to those? Because those are the ones that pop up in classical proofs of the comparison principle. So the hope, it's not actually true, but the hope, at least our hope was at the beginning, that we could only, that we only need to bound the Hamiltonian on these test functions. Okay, then you have a candidate equivalent of this test function of Wasserstein space is the square distance from a given point pi. On RD, there is no issue. You compute the gradient. It's still a square distance object. And you have an analogous in the Wasserstein space of this statement. So you believe that the gradient of your f, you take its norm, you square it, you evaluate it in the tangent space. This is still the square Wasserstein distance. Let's now have a look at the energy term, which is the tricky one. So on RD, it's pretty simple. You can evaluate it directly. It's just the gradient of your energy times y minus x. And if your energy is convex, you can easily find an upper bound to this term by saying that this is less or equal than the energy of y minus the energy of x. And actually, this upper bound is the one that you will use to define things in the bigger space. Because, okay, this guy, we don't know what it is. But since we assume that our functional was displacement convex for some k, here I chose k equal to 0, then this term, whatever its meaning, should be smaller or equal than the energy of the base point pi minus the energy of rho. So now we have identified bounds for both terms in the form of Hamiltonian, and we can define our upper bound. Of course, all of this is heuristics and remain heuristics. It's just to motivate the definition of the upper and lower. You can, in analogous way, come up with a lower bound, and then the comparison principle that you can get is as follows. Suppose you take a functional satisfying the Mechan's condition, which is a classical condition in optimal transfer. So it's made of 3 pieces. You have an internal energy, a potential energy, and an interaction energy. So for the 2 potentials here, you just assume that their Hessian is lower bounded and they are sufficiently smooth. And for the internal energy, you have this typical assumption in optimal transfer. For instance, it would work if the internal energy is the usual Boltzmann entropy relating to Brownian motion, but it would also work if you were considering Rényi entropies in relation with the porous media type equations. And the comparison principle that you can get is that as soon as you have the Mechan's condition, and as soon as your running cost is bounded and uniformly continuous on W2 balls, then there is at most a continuous function that is at the same time a subsolution for the upper bound and a super solution for the lower bound. Okay, so this is as much as I wanted to say about complicated infinite dimensional spaces. So now I would like to go back to finite dimensional spaces, possibly even in discrete. So really, we reduce the dimension. And I would like to present a contribution about functional inequalities for discrete Markov chains. So once again, to motivate the upcoming discussion, I would like to recall what the picture is for Kolmogorov diffusions. So for Kolmogorov diffusions, there is a very beautiful result that tells you that it is equivalent to have a lower bound on the curvature and to be able to construct a contractive coupling, namely, for any pair of points on your manifold, you can construct a coupling of the process starting from X and the process starting from Y in such a way that almost surely the distance between the 2 processes will decay exponentially fast. So this is really nice. You have equivalence between a geometric condition and a purely probabilistic condition. And in particular, it establishes a connection between couplings and functional inequalities, because this is telling you that as soon as you have a contractive coupling like this, then the logarithmic Sobolev inequality holds. Why so? Because this is equivalent to this, and it is well known that the Bakry-Amri condition implies the logarithmic Sobolev inequality. So of course, once you see this, you're very tempted to see if you can replicate some of these results in the framework of continuous time Markov chains. And actually, this motivated the development of several notions of discrete curvature. So there are some that are more based on optimal transport, some that are more based on probabilistic criteria. Each one has certain advantages and certain disadvantages. And there has been a lot of progress in understanding how, the picture for continuous time Markov chain. But still, there are some relatively simple questions that remain, to the best of my knowledge, largely unanswered. In particular, whether or not a contractive coupling imply the log Sobolev inequality, or rather it's the discrete counterpart, which is called the modified logarithmic Sobolev inequality. So this question is still, to some extent, open. And I have tried to give some answers to this problem. And I would like to present you in a very, very simple setting. So I will not at all try to give you the result in full generality, the type of answers that you can get. So here I will work on the 2-dimensional lattice. So I consider random walks on the 2-dimensional lattice. So the random walk is fully specified by the jump rates. See, the xy is the rate at which the walker at x jumps to the vertex y. So once you have the rate, you can also construct your generator by mixing up the rates with the discrete gradients. And here is the result that you can find. So take a continuous Markov chain, which is reversible on the square lattice. Then there is equivalence between a geometric condition on the jump rates that you could vaguely relate to a curvature condition, but okay, let's not be so ambitious for the moment. I will come back to this condition in a while. So there is equivalence between this and the fact that for any pair of neighbors, x and y, you can construct a coupling of the random walk started from x and the random walk starting from y in such a way that the two random walks never get a distance more than 1, and the probability that they have met before time little t is larger or equal than 1 minus this exponential of minus kt, where k is something that will come out of the geometric condition on the jump rates. Moreover, you also get that the existence of this coupling gives you back the modified logarithmic Sobolev inequality for the reversible method. So at least in this simple setting, you can show that the existence of a certain coupling implies the modified logarithmic Sobolev inequality. And actually, the technique that you use to prove this, you can see that it's rather general and it works in a variety of examples coming, for instance, from statistical mechanics. Okay, so let me walk you through the geometric condition on the jump rates. So now there's just essentially only pictures from now on. So what do we require on the jump rates? So let's fix two neighbors, x and y. The first condition is that the rate at which y jumps on top of x is larger or equal than the rate at which x jumps along the same direction. And I store the difference between the rates in this green arrow that I call a good term. And the second thing that you want, you need first to look at the jump rates on orthogonal directions to the xy direction. And you select those directions along which x has a higher tendency to jump than y. So for instance, here you will forget about this direction because y has a higher tendency to jump, but you will keep this direction because x has a higher tendency. And you store the difference in the jump rates in this red arrow, and you call the red arrow a bad term. Now, the condition you want to impose is that the good term is able to overcome the overall contribution of the bad terms. And then you also need to impose the same condition reverting the roles of x and y. So you will ask, so I will go quickly here because it's essentially the same thing. You will ask that x has a higher tendency to jump on y than the rate at which y jumps along the same direction. You select, you now include the orthogonal directions. You select the directions along which y has a higher jump rate. You isolate the corresponding bad terms, and you ask that the good term, which is as usual the green arrow, is able to overcome the bad terms. So this is the geometric condition on the jump rate. So if you have this condition, then you can construct a nice coupling. And it is exactly the coupling that I have shown here. So that I've outlined here. So the two processes never get a distance more than 1, and they coalesce exponentially fast. And let me just tell you what the support of this coupling looks like. Actually, the support of the coupling, indeed, you could see that characterize the type of coupling that you're constructing. So a coupling, so we have two walkers, the walker starting from x and the walker starting from y, and they move in the same probability space. So let's see what could happen at the first time at which either the first walker or the second walker jumps. And actually, there is a pretty rigid structure. There are not so many things that can happen. So one thing is that the two walkers, they jump in parallel along the same direction. So when one of the two jumps along the direction, the other jumps at the same time and along the same direction. then it could happen that the walker, the X process, tries to escape from Y by jumping along a vertical direction. So it tries to use one of these bad terms in order to get away from Y. But then Y reacts to this and it jumps on X in order to keep distance 1 from the X walker. And if you look from afar, then you would see that the two walkers are jumping around the perimeter of a square that contains the edge XY. And the same thing could happen inverting the roles of X and Y. So here you have that Y tries to escape from X by jumping along a vertical direction, but X is able to react to this using his good term and to jump onto Y in order to stay at distance 1. And once again, you will see that the two walkers are walking around the perimeter of a square. And then the last thing that could happen is that they meet. And the probability that they meet is exactly related to the log Sobolev constant. So either they meet at X if X doesn't move and Y jumps on top of X, or they meet at Y if Y doesn't move and X jumps on top of Y. Okay, so this is the coupling support. This tells you how the coupling works. So after the first jump, since they always stay at distance at most 1, everything starts afresh as from time 0. Okay, I would like to conclude my presentation just by giving a couple of perspectives on future research. So the geometric condition on the jump rates that I presented, when you apply a diffusive scaling to the random walk generator, is expected to converge to L1 contraction for Kolmogorov diffusion. So the L1 distance between X and Y is just the distance between the sum of the absolute values of the distance between the coordinates. Okay. So this is what you're tempted to believe, and I mean, it's reasonable that this is true. And the good thing is that you have a non-trivial limit. So your discrete condition will scale to a non-trivial condition on diffusions. But on the other hand, you could also check that this condition here is more demanding than the Wasserstein contraction, which is the Bakry-Emery condition. So it is non-trivial, but it is more severe than the Bakry-Emery. So there is, a priori, there is still room for improvement of on this result. And whether or not the improvement is actually possible, this I don't really know. But a priori, you could do better. But even before starting to wonder about what's the relation between coupling and log sob, what I find very interesting is that there are some very natural questions that are purely of probabilistic nature that still do not have a clear-cut answer for Markov chains. So let me explain this. What gives you the equivalence between curvature and Wasserstein contraction in the continuous setting is the so-called synchronous coupling, so a very simple coupling if you're working on RD, or the coupling by parallel transport if you're working on a Riemannian manifold. So those are the coupling that tell you, oh, contractive coupling is equivalent to Bakry. Actually, if you think a little bit about it, there is not really a clear notion of what should synchronous coupling be for a continuous time Markov chain. And if you toy around a bit with some examples, you can realize that there is more than one candidate, and it's not so clear who does the job better. And even more, even the good candidates seem to have, so it seems that it is much harder to have a contractive coupling on discrete structures than to have it on continuous structure. And so if you answer this, then you probably can have a better understanding of the relation with functional inequalities. And you can push this a bit further. So there is another very performing coupling for diffusions that gives you lots of information on the ergodicity of the corresponding process. This is the coupling by reflection. But what is the analogous of this in a discrete Markov chain? So there has been some advances for jump processes in some concrete examples, but there is not an abstract construction of what is reflection coupling on a graph with certain symmetries, for instance. Okay, This is all I wanted to say, and so I thank you all very much for the patience and the attention. Okay, that's it.
Thank you. Yep. Thank you, Giovanni. So now this is time for questions. I recall to all of you that there were 3 referees for this habilitation. I guess that everybody has received the email from Giovanni with the reports. If not, please tell it to me, and then I will send you again the email. And so the 3 referees were Thierry Bonino, so a local referee, Jan Maas, and Giuseppe Savare. So the latter 2 are external referees. So we are going to start with those 2 external referees for the questions. So Jan, could you start with your questions if you have?
Yes, sure. Thank you very much. Yeah. Okay, so let me mention first that I read the thesis with great pleasure. It's really a very impressive file with lots of interesting contributions to actually quite a wide variety of topics. So this is very nice. I do have some questions. For instance, connected to what you talked about at the final part of your presentation. So you mentioned about the relation between contractive coupling and MLSI. So your construction that you described was on the 2-dimensional lattice. So can you maybe comment how general this is? Can it be extended to arbitrary Markov chains?
Yes, so it works on the lattice of any dimension. Of course, I would say one of the things that I regret a little bit is that the higher the dimension, it's going to be a bit more complicated to satisfy it, because you have more orthogonal directions, and those are bad. Actually, what I think should be the right condition. So the thing is that I will try to explain it in a drawing. So if you have 2 guys that are neighbors in the lattice, say X and Y, then essentially the only move that X can do to get closer to Y is this move. So any other move will take him further away from Y, and Y has to react in some way to keep at distance 1. But now suppose that you accept that people get at distance 2. So suppose that so Y is willing to accept that X goes at distance 2 from him. So he jumps here. Then when you're in this situation, things get much better, because X now has 2 moves that will approach him to Y. And you can imagine that this condition here is actually kind of dimension free. So I think that I think that this is the right condition under which you can prove that you have a coupling that scales to synchronous coupling with the good contraction properties. Now, whether or not this question implies, whether or not this condition implies convexity of the entropy in some sense, this is a longer shot. Because of course, somehow the beauty of working with guys that never get a distance more than 1 is that, at least at the heuristic level, you have some kind of gradient estimate for the semi-group. Whereas if you're accepting to work with people that are distance 2, then you will work. So what you can obtain are kind of average gradient estimates, and it's very delicate with the discrete Bakriani calculation. So if you change things by a little bit, you could screw it all up. So so this is what I expect to be true on lattices. By the way, I think that nevertheless it would be nice to have a functional inequalities that is associated to this kind of condition. So this kind of where you allow people to get a bit further than 1. maybe this functional inequality will not be exactly MLSI. It will contain some bad terms that will vanish in the limit. I think that would already be, given how hard it is to prove MLSI in this context, I think that will already be very nice. Then if you move away from lattices, actually.
So maybe if I can ask about this modified condition, would you expect to see the Euclidean metric in the limit, or would it still be sort of more L1 related?
No, the hope. But okay, don't take my word for granted, but the hope is that you will get something Euclidean.
Okay.
Yeah, that's my hope. Yeah. Okay, and about robustness of the condition to other graphs, actually, I think one thing that I should probably also have done better is that whatever the graph, the technique and the condition is essentially always the same. So, okay, no, maybe, sorry. If your graph does not contain triangles, so if your graph has only, the loops are only squares, like this generalized birth and death change, like hardcore models or easing and stuff, then the proof is essentially always the same. Nothing changes. Because, yeah, you can always relate to a coupling, essentially with spins, is if one guy changes a spin, then the other changes another spin in order to always have at least one spin of difference or stuff like this. Where things get really bad is when you have triangles, like in conservative dynamics, like zero range. There, the technique I have, okay, it still gives you results, but for random walks, the thing that I was really interested in, it was that the condition I get is non-perturbative. So it doesn't necessarily work for measures that are approximatively product measures. Whereas for zero range, it's kind of perturbative. It's okay, more or less like the condition that one can find in your works or in other works. Yeah, I hope this answers the question. Yeah.
Yes, definitely.
If there is more, I can.
Yeah, so if I may continue with a question, yeah, then so if you apply your criteria to discretizations of Kolmogorov diffusions, how far is your condition from the lower bound on the Hessian in the continuous setting?
I think that. So my condition implies convexity of the potential, and I think it will give you a. So okay, I'll try to explain this. I think it will work. So suppose that V is your potential. So my feeling, I haven't fully carried this out, but it will work as soon as the smallest say. So you have enough convexity. So lambda mean is say large enough. And then there's something a bit strange that happens that I still don't fully understand. But this is, once again, I think you will really understand very clearly once you relate my condition to L1 contraction. But it will work always as soon as lambda is large enough. So the smallest eigenvalue is large enough. And so V is convex, and the cross derivatives are non-negative.
Okay.
So this is a bit unconventional, right? Because so pointwise, and this amounts to the fact that you can. So this is the condition that allows you to do this operation where you chase down the walker that tries to go away from you, and I think actually that this is. So the fact that you can keep track of these terms when you do the usual discrete Bakry-Emry business is the fact that is really what makes it possible to have non-perturbative condition. So when I had this list of moves, the fact that you take care of the moves that allow you to chase down somebody who is trying to get away from you, these are the ones that, in my interpretation, allow you to go to non-perturbative setups. Yeah, so this is what I expect.
Okay, thanks.
Thank you.
Any other question, Jan?
Yeah, I could ask more, and I'm not sure what the procedure is, whether we go around or.
No, you can ask as many questions as you want. But
Okay.
so if you have more questions, please do.
Okay. Yeah, maybe a small question related to a different part of your presentation. So, in your results related to this turnpike phenomenon, so there were some unspecified constants in front of the entropy term. So you had some amount of.
I know that. Yeah, you can. Yeah.
So are they sort of explicit or?
Yeah, they are explicit, but and they're good in the sense they are small with curvature. Yeah.
Okay. Yeah.
They are explicit. There are many ways of writing the result, depending on how many things you want to leave implicit. So actually, I replay. So instead of this, so the sum, of the marginal entropies, you could just write the entropic transportation. Actually, in fact, you can write down this turnpike estimate in such a way that if nu is exactly the push forward along the gradient flow of mu, you get back exactly the Bakry-Embry dissipation result.
I see. Okay. Okay, thanks.
Okay, thank you very much for the question.
Jan, you just tell me whether this is fine for you or if you want to say something else.
Yes, I'm happy. Thanks. Yeah.
Okay. Thank you, Jan. Thank you so much. So the next person is Giuseppe. So who is the second external referee? Giuseppe, if you have any questions, please.
Okay, thank you. So I agree with Jan with the nice opinion on what you explained to us, and I have just a question about the part on controlled gradient flow problem in Wasserstein space. It has a structure which is has many relation to the Schrödinger problem. But what are the main differences, for instance, concerning if you have studied this part, what are the main differences concerning, for instance, the regularity of the solution of this controlled problem? So it enjoys the same nice smoothness like solution to the Schrödinger, or there are more difficulties?
No, okay. By the way, maybe let me just clarify a little bit. The difference with the Schrödinger problem here is kind of minimal in the sense that, okay, the big difference is that I don't have the terminal constraint here. This I got rid of. And to make things non-trivial, I have added this running cost. So all of our method and results are like geometric and metric. So we never really write down any TD. So actually, that's the only way you could hope, in my opinion, to get the uniqueness of viscosity solutions. And to answer your question, I'm really not sure whether or not this propagation of regularity at intermediate times will hold when you move from Boltzmann entropy to something else. It's really something that you don't see through the.
And if you keep the simplest situation, Boltzmann entropy and perhaps H equal to 0, so you are sort of infinite horizon version of Schrödinger.
But then in that case, so if I set H equal to 0, then the solution is the gradient flow. The best thing is to do nothing. So yes, in that case you get a lot of regularity, but it's a bit of a cheat. Yeah, no. So for us it was really actually okay. one day we would really like to be able to write down. So now we know how to solve the Hamilton-Jacobi equation. So the corresponding PDE would be the characteristics of this Hamilton-Jacobi equation. So we would be really happy to write these down and then to see that those are PDEs. So we know what PDEs are the candidates. The thing is, so the characteristics should be associated to the gradient flow of F, of this energy F. And what we can say about this energy F is that it's Lipschitz. So this thing is over less or equal than K, uniformly in space. This is not too hard if your gradient flow has nice contracted properties. But at least, yeah, you probably know much better than me, but at least I don't know how to write down the gradient flow of an energy that is just Lipschitz. But if there were ways to do this, I think it would be great.
Yeah, I was confused, since in fact the interesting case was the opposite. So E equals 0 and H equal E. Since this is funny, since this kind of functionals, when you rescale also time, has been used by De Giorgi to study gradient flows. The gradient flows of H, in fact, as a limit.
I see.
And so I was interested in the fact that what happens about regularity when of solutions of this this problem. Yeah.
So you would like E to be displacement convex?
H to be displacement convex.
Yeah, okay, in that case, I kind of also don't know. And the reason is that the problem you end up is very different, structurally very different. So even if you were to study the uniqueness of viscosity solution for the associated Hamilton-Jacobi equation, it's really completely another story. Because if you see the way we guess the upper and lower bounds here, we really use the fact that we have this term in the Hamiltonian. If you do what you're suggesting, you would just have the energy instead of this guy in the Hamiltonian. So I think this Hamilton-Jacobi equation has been studied. So there are results about this one. I'm not the most expert, but somehow it falls out of the analysis that we are doing here. It's a bit of a different problem. It would be super, I think, yeah, it will be super interesting, but it's probably not really related to this control gradient flow. So for us, it's really key that the displacement convex part is in the dynamics and not in the cost.
I have another question. You showed us you have shown this asymptotic behavior where in the limit you have the integration of the Fisher information along geodesics.
Yes, yes, here.
Yeah, exactly. So this is really interesting. But in this case, you are assuming that this integral term is finite, or you may use this property to gain some control on this term.
No, we need, so actually, okay, the estimate also works if this guy is infinity, but it tells you that there is no second order term. But no, you need to assume that that it's finite. And of course, it's not, so there are many cases where you can show that it is finite, but it's not so simple. It is finite. It's to have a very good understanding of when this is finite or not. It's pretty hard because, okay, no. Maybe I can say something that we have been thinking a lot about with Luca. So the Fisher information, of course, is not displacement convex. So if you have finite Fisher information at the beginning and finite Fisher information at the end, there is not much that you can say about this object. So what you can definitely say is that as soon as you're not along a geodesics, but you're along a Schrodinger bridge, this is finite, but this is kind of by definition. But what seems to be true is that, okay, the Fisher information is not displacement convex, but it seems to behave like a displacement convex function if the measure mu0 t is log concave. So in a way, it seems that log concave measures can heuristically be interpreted as points where the Fisher information is convex. So we have a very, very long formal calculation that shows this.
Mu0 t log concave for every t along the geodesic.
Yeah. So if you yes, exactly. If you can show that, or you don't even need log concave. You just need the log of the Hessian to be bounded above, even if it's bounded above by a positive constant. It's not a big deal. Yes. So we have been really wondering about how to interpret this. I would really be happy to discuss more about it, but okay, somehow the calculations are a bit, they are not really inviting, but maybe the message is, it seems that you can interpret measures was log Hessian is bounded above as points for the Fisher information as a lower bound on the Hessian. So what do I mean by this? You take a log concave measure, you take a small geodesics originating from it, you evaluate the Fisher information along this geodesic, then the second order derivative at 0 seems to be positive, or at least controlled by a constant.
This is reasonable, since if you, at least in a flat situation, log concave measures corresponds to RCD 0 infinity condition. So
yeah, I would love to know more about this.
Okay, I'm fine. Thank you.
Thank you. Thank you very much.
Thank you. So the next referee is Thierry. Thierry, do you have any comments or questions?
Yes, thank you. Actually, my first comment is to say that I was very impressed by the manuscript, and actually all the beautiful connection and very deep connection Giovanni was able to establish between plenty of point of view, geometric point of view, transport and stochastic differential equation and infinite gains and so on. So I think it was really impressive, and I really enjoyed reading the manuscript. I have a few questions. I'm not sure if there are relevant questions for now, or whether the answer might come in 10 years' time. So some of them may be possibly too vague. One of the issue you're using a lot, Giovanni, is reversibility. And so, of course, if you think in terms of the turnpike problem, for example, you would expect that it holds, not possibly in full generality, but for many non-reversible systems. And one of the open issues you mentioned during your talk was to say, okay, maybe I can implement also some couplings or some variation if I have only a local structure, and I imagine reversibility would non-reversibility would fit within this global framework where certain things should hold, but possibly locally, or so okay, I was wondering whether you have some comment to say in this direction, either for the turnpike or more generally for a lot of things you've been implementing on the Schrödinger problem.
Yeah. Okay. So thank you very much for the question. Of course, reversibility plays a key role to have the optimal transport interpretation, because you want velocities to be gradients. And if you don't have this, at least to the best of my understanding, the whole Riemannian viewpoint kind of breaks down. But exactly as you are saying, and I think it goes a bit in the spirit of what I was saying about the turnpike. So you can just use this optimal transport as a way to find big categories into which certain control problems fall, and then try to resort to more probabilistic techniques to analyze them when the geometry is not really helping you anymore. And I think that at least for the turnpike phenomenon, you can work outside of reversible assumptions. So we kind of already starting doing this a little bit by working on the kinetic version of the Schrödinger problem. So the reference there is Langevin dynamics, that is not reversible. And essentially, most of the things go through using a probabilistic perspective. So in order to get your gradient estimates, you use couplings, and things seem to work fine. Also, for this FBSD interpretation, I think there is no need of, so reversibility doesn't really play a role. For all these Newton's law things, yes, of course. Somehow the big question is, can you kind of come up with a geometry on the space of probability measure that is associated to a certain interaction mechanism and can this geometry take into account irreversible dynamics? I don't know the answer. Somehow, maybe I'm wrong, but as far as I understand, even if you take uncontrolled processes like stochastic differential equations without control, and the drift is not a gradient, I don't know of any particular insightful variational interpretation of this. So somehow the problems seem to be present even at a simpler level, even though I may be wrong here. I'm not so sure, but I'm not aware of nice geometric interpretation of gradient flows for irreversible stochastic differential equations. Yeah, maybe to summarize, I think as far as it goes, as long as it goes for the quantitative results, like turnpike or even functional inequalities, I think a lot can be done without reversibility. When it comes down to writing down the equations in a geometric structure where everything works nicely, this I'm not as confident that it could be done.
Yeah, I agree that when you start to go into this world of non-reversibility, you can't ask question in full generality. So indeed, after to hopefully have some physical interpretation, you may want to start from some more specific.
Yeah, maybe on examples. Yeah, I think maybe on examples, it's a good way to. Maybe if you take one example and you really focus and try to establish the analogy with the result you have in the reversible world and how to modify them in the non-reversible world. Maybe there is one example. Okay, maybe where I looked is instead of minus gradient of u in the classical Schrödinger problem, you have a drift field B that is not gradient. Can you make sense of the corresponding? So you take the corresponding optimal curve. You still denote it by the t. Can you write down something like a Newton's law in this case? And what seems to be true is that you can, if you look at the marginal flow only, you can. So you use the same geometry as optimal transport. So you'll have acceleration equal. So you have the first term is the same that you would have without the bad guy here. So you have gradient of Fisher. And then you will have a term that you could possibly interpret something like a viscous force. I don't really know how to say this. So you have a term that is some term, I call it F, that depends on B and on the velocity. So it's not really Newton's law. It seems that you gain an extra term that depends on the velocity. So this is at the level of the geometrical interpretation. So what if you do some formal calculations, it seems that adding non-reversibility here means that in the Newton's law, you will pick up a further term in the acceleration field that is not related to position, as here, but is related to velocity. But whether or not this is like a kind of something pretty special to this special example, or it's more general, this I don't really know.
Okay. Thank you. Maybe one another question in this case related to more specific example, and that's something you mentioned at several points is our lattice gas. I mean, extending this Schrödinger problem on some lattice gas, or even you just mentioned the other part with where you have triangles where you're coupling with zero range. So what maybe if you could tell us some perspective or some thought about how to push what you've been doing in this.
Yes. Actually, this would be really nice to advance in this direction. So for lattice gases, like a simple exclusion. Okay, if we let's start with the underlying dynamic to be reversible. So we take a simple exclusion without the thermal reservoirs. Actually, at the thermal level, everything works very nicely. So we can write down optimality conditions as a system of coupled PD systems. You have all the nice relations that you have for Schrödinger bridges in the standard case. And what is, in my view, particularly nice is that what you realize is that when you study lattice gases and the associated large deviations, actually it seems that you're kind of moving from the geometry of optimal transport to another geometry that is the one dictated by the so-called mobility coefficients in the lattice gas. So what do I mean by this? So Wasserstein distance is the one that you get by solving for this variational problem. And here you have the continuity equation, and you start from mu, and you end up in mu. So it seems that in order to have the exact same picture, so Newton's law, nice symmetry relation in the optimality conditions, for lattice gases, what you need to do is to work on a different geometry. So it's the one where instead of mu here, you have a function that depends on mu. Sorry. And if you correct your geometry, then virtually the problem is exactly the same as before. From a geometric standpoint, there is nothing that changes. So turnpike, all these kind of things should hold. The problem that we have is that the PDEs that correspond to optimality conditions of the problem in fluid dynamic form are PDEs that look a bit like the kind of PDEs that you would get in min-field games. But as of now, we are not able to prove existence of solutions in a rigorous fashion. Mm-hmm. And I expect this to be possible, but I've tried a little bit and couldn't and couldn't do it. So I think that somehow, if you could unlock this technical step, so getting some kind of solution for the optimality conditions in fluid dynamic form, then you will kind of open a whole new field. So no, that's too much. But you will open a lot more new perspectives where you could work. There is one result that seems to be applicable even in this framework. It is the Hamilton-Jacobi equation that we studied. Okay, so let me go back here. So here I said that the controlled controlled gradient flow problem has to be set in the Wasserstein space. But actually, in the article, the result that we have does not necessarily need the control problem to be set in Wasserstein space. So you have a more general set of assumptions, which essentially boil down to the following: your functional and energy functional must admit what people call an EVI gradient flow, and you need to have directional derivatives along nice directions. So you need to have this limit exists if mu h is a sufficiently nice curve. So if you have these two assumptions, the result would work, even if the underlying geometry is not the Wasserstein geometry. And we have not checked yet, but it seems that, by the way, using some results of Giuseppe, it seems that if you consider the geometry, for instance, of the simple exclusion, everything falls through and you have uniqueness for the corresponding Hamilton-Jacobi equation. So this is the first rigorous result that seems to be really at hand for the lattice gas. And the second one would be optimality conditions for the problem. And for that one, yeah, some work still needs to be done. So one could try with a like a variant of synchron algorithm. So try to replicate the synchron procedure on mean field problems. So you can at least formally write it down, but then you have to show convergence, and this is still not super clear. But it's definitely something that I would like to, to explore in the future.
But so far, or at least I would expect that the form of the chi plays a role. I mean, here and so on. It's otherwise you might just end up with phase transition and.
Yes, of course. No, it doesn't work for whatever chi. Yeah, typically you want chi to be concave, and you want to stay away from phase transition. You want a unique steady state. Yes, sure. Yeah. Yes. No. You cannot account for whatever chi. No, that's for sure.
Okay, thank you. Thank you very much.
Thank you.
Thanks.
Thank you, Thierry. So now this is time for questions from the members of the committee. So let us start with Annabella. Annabella, do you have any comments or questions?
Yes, thank you. Well, first I'd like to say I'm going to repeat a little bit the words of Thierry just before, but I'd like to say that I was really impressed, and it was a pleasure to read the manuscript. It's really a very nicely presented piece of work and very impressive work. And also the exposition today was very nice. So thank you, Giovanni, for this. I had a few questions actually when I read the manuscript. So let me try to make some order in this. One of them is connected with the non-reversible cases that were discussed just before. So so I would like to know something you just said. I mean, you consider this B and in the drift, and you said something, but I mean, somehow what is the price to pay? The question was, but maybe you answered already. What is the price to pay if you don't consider gradient type drifts, right? And this question, just before you answer this question, in my spirit is related to another one, which is instead of considering RD or something as the underlying manifold or some finite dimensional manifold, what about consider an infinite dimensional manifold to start with? And these questions for me are sort of related in my spirit, because I have tried to work with things like that in the case of Navier-Stokes equation. So.
Okay. Yeah, are there more questions?
Yeah, but don't
okay,
you want
okay, sorry. No.
I mean, I can put it down, but
yeah. So again, to move from so the price to pay to move to non-reversible to the non-reversible setting is really that the Riemannian geometry viewpoint is either lost or at least much harder to establish. And this viewpoint is really kind of crucial in many calculations I did, because it reduces some kind of involved computations to some simple computations on a one-dimensional toy model where you understand everything. So this is really the price to pay. Actually, as I said, if you don't care too much about having this Riemannian geometry interpretation, so about writing down this Newton's law, then there are many things that you could do. Like the turnpikes, like the FBSDs, they're not really sensitive to this, at least I don't think. So in a nutshell, really the only thing that you really lose is the fact that you have this nice Riemannian viewpoint. That's the thing you lose. Concerning infinite dimensional manifolds, infinite dimensional manifolds as underlying state space, I've never really thought of it, to be sure, to be honest. It will be, of course, pretty nice. I expect there to encounter quite some technical
Sure.
maybe something I didn't really highlight on my presentation is that, okay, I always wrote down these equations, took many derivatives as if I could, but even for finite dimensional manifolds as a base space, showing, for instance, the existence of dual potentials for the Schrödinger problem tends to be rather tricky, much more than one could expect. And I don't know.
I'm not expecting maybe a general theorem for general infinite dimensional space, but in specific infinite dimensional cases, I would say.
Yeah, that seems more viable. But okay, I've never really given a serious thought about this. Yeah. I get. Okay, no, I don't really have a.
If you do, please send me a message because it would be helpful for me. Anyway, another question: you don't consider manifolds with boundaries, right? So
no.
To consider stopping times or reflective Brownian motions or things like that.
No.
Okay.
No, for the moment.
That could be probably possible to consider, right?
Yes, actually, there is something that I've been thinking a little bit about, which is a variant of the Schrödinger problem where you include stopping time, and it should go as follows. I don't write down the math. I just write down so I just tell a little story. So in the Schrödinger problem, you have your particles and you take a picture at time t equal to 0, and then you say, okay, I take another picture at time t equal to capital T, and then conditionally on this information, I have to look for the most likely evolution. But then you could think of a different problem. So you have your picture at time 0, and now suppose that this is the space where particle lives, and now on this space, you have, say, a barrier like this one. And then you say, okay, I wait until the moment each of my particle has hit the barrier. So I define a stopping time. And I condition on the observation of the particle configuration when particles hit the barrier. So it will be a probability measure that is concentrated on the on this barrier. And then you say, okay, conditionally, so suppose like, you have I don't know, a sheet of paper, and you wait until the particles hit the sheet of paper, and you observe the configuration of the particles when they hit the sheet of paper. And then the question will be, okay, conditionally on seeing the picture that the particle have left on the sheet of paper, what was the most likely evolution? And I suspect that this will end up being a stochastic control problem where you still control the drift, but up to a stopping time and not up to a deterministic time, as in the classical Schrödinger. So I think that this could go probably in the direction of what you're suggesting.
Oh, okay. So this again is something that's going to interest me a lot. Maybe I'll send you a message after.
Thank you.
Okay. I have, I think not to exaggerate the questions, I think I have 2 more questions, one and a half. One is a real question because I didn't quite understand, or I'm not sure I understood. In your manuscript, can I refer to a page and?
Yeah, sure.
Okay, that's page 21. And then you have vector fields along curves.
Yeah, let me look it up.
Yeah, I'm sorry.
I hope it's not a typo.
No, it's just me.
Okay.
I mean, it's probably obvious for you, but it was not for me. So page 21 in the middle, it's
Yeah.
vector fields along curves. And then it said it's not possible to define a notion of covariant vector fields on P2. Why is this?
Oh, yes.
It's not a typo at all, bro. Certainly.
So why you should restrict to define this along curves and not? Yes. So okay. The answer would be pretty technical. Okay, what I can tell you maybe is that all of these constructions, they rely on the fact that you can view the space of probability measures as a Riemannian manifold. And as I told in my presentation, the first step in order to do this, you identify the tangent space with the space of gradient vector fields.
Yes.
But this identification is actually, so how should I say? This identification is only possible if the measure mu is somehow regular enough.
Mm-hmm.
So the fact that you can view the space of probability measures as a Riemannian manifold is true only formally. It's not a true Riemannian manifold. And therefore, as soon as you want to start doing a construction that you would do on a general Riemannian manifold, so a global construction, then you run into many issues. And as I said, this is really because the identification of the tangent space as a space of gradient vector fields is not true everywhere. Okay, this is one of the reasons why. There are more.
Okay.
So all in all, the thing is so you can carry out local rigorous constructions along curves, but global rigorous constructions, I don't think you can do this.
Okay, this is just my ignorance on this technique.
Yeah.
Okay, so this is my last. It's a half question because it's not a serious question. It's just you know that you have already from the beginning. You say that you have three formulations of the Schrödinger problem.
Yeah, I think I was trying to say.
And the one of them, I mean the last one today, actually, in terms of equations, in terms of the Fokker-Planck equation.
Yeah.
You don't need it. This is just, as I say, it's a half question, or even less. You call it fluid dynamic formulation, and I mean the question: why fluid?
I think it's
where does it come from?
It's a termination that I borrow from optimal transport. So if I kill the Laplacian in my fluid dynamic formulation, then what I get back is the Benamou-Brenier formulation of optimal transportation that is often referred to as the fluid dynamic formulation of optimal transport. And I think this owes to the fact that you can imagine the bunch of particles diffusing as the particle composing a fluid.
Okay.
That's, So actually, it's not I just copied it.
No, as I said, this was not a serious question anyway, but just curiosity. Okay, thank you very much.
Thank you very much.
Thank you. So the next one is Arnaud. Arnaud, do you have any question?
Yes, in fact, I have some, but in fact, I have too many also. It was really interesting, Giovanni. Not only your manuscript was a pleasure to read, but also your talk today. So I would just insist on the irreversibility case. Perhaps one thing that you can consider as a special case to be consider B to be gradient U plus S gradient U, where S is an antisymmetric matrix, to precisely see where it can play on your derivation, because it's somewhat expected to have some acceleration for the thing. So you may see something, and I believe that in the special small calculus that you showed you may perhaps see some particular feature in this case, where it may be, where it may perhaps explain really how it accelerates the dynamic. Perhaps it could be really interesting to push a little bit forward this way.
Yeah, that's
definitely.
true. So I think, yeah. So this matrix is something that makes particles like rotate around. Yeah.
So you'll see the rotation exactly, and so see the effect, which would be really interesting, I believe.
Yeah, that's probably the first thing. Yeah, that maybe one thing I can add is that I forgot, the whole discussion about the reversibility. So optimal transport interpretation, as I said, breaks down with when you break down reversibility, but Bakri-Emry does not. So the Bakri-Emry calculus a priori does not need reversibility. So this is also one indication why you could hope to have the results beyond the reversible case. Yeah, sorry.
Yeah, a very general question. You always assume that you've got some lower curvature in Bakri-Emry sense, but nevertheless you consider the kinetic Langevin equation where the curvature is infinite. So why keep this lower bound?
Yeah, actually, so in that case, when we consider the Langevin dynamics as a reference measure, of course, the methods that we used to prove the turnpike properties are inspired a bit by the ones we used in the other problem, but are not the same. So there we used this technology that has been developed over the last years in order to adapt a little bit the Bakri-Emry formalism to the kinetic equation. And okay, when we started, it was really not clear that it would work at all, because, as I said, the geometric interpretation breaks down. But somehow this is just pointing once again at the fact that there is hope to go well beyond pointwise assumptions. So the method and the approach we used for the kinetic problem is really not related to Riemannian geometry and optimal transport at all. And that's why I have hope that we can go further. Still, okay. At the moment, we still have pointwise assumptions there because we still ask that some potential is convex, strongly convex. But I think that if you explore the perspective that is in this slide to work a bit with coupling methods, there is chance that you can go beyond.
The real assumption that you suppose is that in some sense entropy is decaying, no?
Yes, actually, the real assumption that you impose is that the unconditional particle system is strongly ergodic. And actually, maybe there is also one thing I should say is that here I presented your turnpike estimate with the entropy, because somehow this is like the coolest you can hope for. But if you can be less ambitious and try to establish turnpike through a Wasserstein type distance or a modification of the Wasserstein distance. And in that case, I think you can really weaken the assumptions quite a lot. So,
okay.
So the overall idea is that the ergodicity of the underlying particle system is the one that should.
So you can do something when your dynamics is only polynomially ergodic.
We did something with Yvan and Gauthier,
okay.
Assuming the CD0n condition.
And CD0n, you're exponentially ergodic.
No.
If n is positive.
So, okay, maybe it's a matter of terminology, but CD0n for me is the Brownian motion, and it's not really exponentially ergodic.
Ah, you mean, okay.
So there we can have, for instance, polynomial decay of the Fisher information. Polynomial decay of the Fisher information along optimal curves, and we can have kind of polynomial turnpike estimates. Of course, in that case, you have to be careful because the steady state may not exist. So you have to be a bit careful. But okay, maybe one thing I feel like saying in this polynomial business, one cute thing is that you can arrive to a variational interpretation of local Sobolev inequalities like Li-Yao by using this by using this geometric viewpoint on the Schrödinger problem. So typically, optimal transfer gives you a nice interpretation of integrated inequalities like log Sobolev. But if you want to have a nice geometric view on the local inequalities, which are of course stronger, at least to the best of our understanding, there was not an optimal transfer way of doing it. But if you combine optimal transfer with the Schrodinger problem, then yes, you can do it. And actually, the local Sobolev inequality, you can interpret it as a kind of a turnpike estimate, if you want. Yeah.
Oh, okay, just one comment on your things on Markov chains. There have been some coupling techniques developed by Eberle and Micah for generalizing the idea of reflection coupling or construct particular coupling. And for example, for what Jan suggested to consider approximation of stochastic differential equation, they really used some type of reflection coupling, but it's for very particular examples. So
yeah, as I said,
it will.
Yeah.
Well, it will be nice to be able to get some very general ideas of a synchronous or reflection for general Markov chain, but I believe it's quite difficult to be very, very general.
Yeah, no, I think it's quite difficult, but maybe there are some recipes that are more general than the ones that are. Yes, it's true. As I said, there is some work for reflection coupling for jump processes, but it's a bit on specific specific examples. And in particular, I think there is not much known because if you take those systems coming from statistical mechanics, for instance, zero range, just to name one. What is synchronous coupling there? Okay, it's kind of clear. You have this attractive coupling. But what is reflection coupling and how should it help you to get nice estimates if you go away from this attractiveness condition? This is still, to my understanding, it's not really known. And I think it would be really nice because somehow, if there is one, it shouldn't be too complicated because usually it's how it works with couplings. If it works, it's simple. So if there is one, it should be easy to find.
We will discuss that a time, I believe. So thank you once again.
Thank you.
Let the other get comments or questions.
Thank you, Arnaud. Nathanael?
Yes, thank you. So first, let me say that I also really enjoyed the presentation and the manuscript and all the diversity of results obtained by Giovanni. So I have some questions about entropic Talagrand inequalities. So you explained that they are stronger than the classical Talagrand inequality. So can you see how strong they are at the level of concentration? So can you, do you think you can use this entropic Talagrand inequality to improve something at the level of concentration for the underlying probability measure?
So with Luigia, we established that this entropic Talagrand is equivalent to a certain kind of dimension-free concentration. But it's, now that I think about it, if I recall well, the usual concentration inequality, you have a set, and then you state the concentration inequality in terms of some enlargement of the set, right?
Yes.
At least in one of the interpretations. And the enlargement, you do it with the metric that is in your space. I think the one we got with Luigia, you use a different enlargement of the set. So suppose this is your set A. I think the enlargement of size U is something like the points such that the probability, let me write P, the probability that your diffusion hits the set starting from X is larger or equal to E to the minus U, something like this. So it's true that, as I said, I said that entropic Talagrand is stronger than Talagrand. So this you can see from the equation, from the inequality pretty simply. But the fact that the concentration of measure inequality that you get by using this type of enlargement is stronger than the one that you get from Talleyrand. To be honest, I don't see it immediately like
Okay.
this. I think it has to do. It must be something like because to pass from the entropic Talleyrand to the classical Talleyrand, you do short time asymptotics. So probably it has to do with the fact that when you let t to 0 and you condition this object should so you condition in ending up in some y, this object converges to a line, and then you should recover the usual Euclidean distance. But I'm not so sure that so okay, this is like how it should be, but I'm not, I can't say right now. So the answer is morally, of course, yes, because the inequalities are stronger. But if I just take the concentration of measure version of our inequality and how it clearly improves the one that you have with Talleyrand, it's not so clear. No, I have to say I don't see this very clearly at the moment.
Okay. And do you have functional versions of concentration? Here you told us about
yes,
version, but you can also maybe
yes,
concentration for a class of functions, maybe related to the semigroup.
Yes, exactly. So yes, this we had. So let me recall. So I think that the usual Talleyrand is in terms of concentration for the Hamilton-Jacobi semigroup, right?
Yes.
And the hour is exactly the same exact result, but instead of Hamilton-Jacobi, is Hamilton-Jacobi-Bellman. So you have a Laplacian inside.
Okay.
So as usual, we just add noise where there is not in the optimal. Yes. So this is clear. Here I can answer. Yes. So it's the same type of property, but you have the Hamilton-Jacobi-Bellman semigroup instead of the Hamilton-Jacobi. And of course, as t goes to 0, you have this convergence. Hamilton-Jacobi-Bellman to Hamilton-Jacobi. And here you really see that at the level of concentration for semigroups, you have the correspondence between the. You can recover one result from the other through a short time limit.
Okay. And I have another, perhaps a bit vague question, but the classical Talleyrand inequality is some sort of Gaussian improvement of a very well-known inequality, which is the Pinsker inequality. So do you think there is some entropic Pinsker inequality with some, I don't know, some entropic regularization of the total variation distance? Does it make sense, or do you think?
So the Pinsker, you mean that the total variation is bounded by entropy? That's
yes, yes.
And you can view Talleyrand as an upgrade of this, right?
Yes, exactly.
I don't. I don't really know. No, right now I don't.
Okay.
So somehow Talleyrand, so the entropic Talleyrand is telling you something like, so usual, of course, maybe I can one thing. Yeah. So the way I see this is that, so this is actually the entropy of the optimal plan against the reference measure. And since the optimal plan has marginal mu and nu, of course, this is always larger or equal than the entropy of mu against n by Jensen.
Yes.
And the way I see this inequality is yet another way to cheat Jensen. So you get that a joint entropy is bounded by a marginal entropy if you pay a price, and the price is a multiplicative constant. No, I don't quite see. So of course, okay, I can see it's an improvement of Talleyrand, and since Talleyrand is an improvement of Pinsker, I can see not much more than this.
Yes, okay.
No, unfortunately, no.
Okay. So I have another question about the discrete setting.
Yeah.
So as you know, probably some people like, for instance, Christian Léonard or more recently Paul-Marie Sanson, so they try to obtain a displacement convexity of entropy along Schrödinger bridges
yes.
So do you have hope to get this type of result in the setting you presented?
Yes. Actually, yes. So to explain a little bit, the calculations I did are not along geodesics, but are along the flow of the Markov chain. So in a way, I'm aiming at a less. I'm aiming at less.
Yes.
So it's not a priori clear that they would transfer to Schrödinger bridges.
Mm-hmm.
That said, I have done some calculations, and in certain models they do.
Mm-hmm.
But and in certain models, I also have the feeling that the conditions I have, they would also extend to the this notion of entropic curvature developed by Jan and others. But whether the full pack of results I got transfers, this I still has to be worked out. I kind of hopeful that it goes so it can work in the framework of Paul-Marie, because essentially he's working with a purely probabilistic perspective, just the entropy, and you have these two forward and backward potentials. And this structure looks pretty much like the one I use for the setting of entropic curvature. There are some a priori choices on the metric to be considered, and this is not super clear to me that my framework would fit in there. But as I said, in certain examples, it seems to work. The thing which seems delicate, once again, is to be able to use somehow. Let me just try to explain this. When you do your convexity estimate, the Hessian of your entropy will contain it's usually lots of terms, and there will be some term that relates to this kind of things in the coupling. So some terms they relate, one guy starts to escape, the other chases him down. So all the other terms, I'm pretty sure that they would work well if I try to implement my method with Paul-Marie framework or with Jan's framework. For those terms, I'm not so sure. Those are the ones that need to be checked really carefully. Once again, all of this is hypothetical, so I believe it's like this, but I don't want to make a clean affirmation.
Okay. Thank you.
Thank you, Natalia.
Thank you. So I think that this is my turn to conclude this session of questions. So the first thing is that once again I would like to congratulate you, Giovanni. This is really impressive what you have achieved. Just a few questions. The very first one is about the HJB equation, or the HG equation, I should say, the Hamilton-Jacobi equation on the space of probability measures and these results that you have for a viscosity solution. My first question is that this is for something that is time homogeneous. So what happens if now I put time in the a finite time horizon in the cost functional?
Yes. Yeah. Thanks. Yeah. Of course, it's very natural to wonder what happens there. You will pick up, of course, a time derivative in the Hamilton-Jacobi. So the reason why we started with this ergodic equation, well, of course, it's a bit simpler because you eliminate a variable. But the real reason is that this is the equation that people who work in large deviation have studied. So we wanted to start from there to be able, on the one hand, to profit a bit from their technology and also to be able to compare with what they were doing. Yes. So essentially, the thing that you need to understand is if you add the finite time horizon, you have to find an upper bound for the Hamiltonian for time-dependent test functions. And it is not unreasonable to think, and this is somehow in our plans, it is not unreasonable to think that the strategy that we have outlined works for so if you take a square test function like this one, where, for instance, let me.
Oh, you are muted. You are muted.
Sorry. Okay, I'm back again. So if you consider a test function like this, where you multiply this guy by a smooth function of time, then the construction of the upper and lower bound would be more or less the same. So that would be the starting point. Then of course, as I said, this is just about defining the notion of solution. Whether the bounds you get are tight enough for the comparison principle, this I don't know yet, but it's definitely somehow in the plans.
And so just to clarify, for the moment you have uniqueness, but you are missing existence, or did I miss something?
Yes. For the moment, so the existence part, we got it wrong a couple of times. So now it seems that we are on track. So there should be also existence. The thing is, okay, here we want to work with functional satisfying the Mechaan's condition. Actually, we would like to work in an even more general setting. That's the one that we use in the paper. So for specific functionals like relative entropy or even the relative entropy plus interaction potential, I think that the existence proof should not be overly complicated, but somehow all our method is based on some rather abstract geometrical arguments that are hopefully quite flexible. So we would like to be able to pull out an existence result within this geometrical framework. And if you go to specific examples, probably things get much more much simpler. So that's why we are still this is still in progress. Of course, we started from Unix because somehow the general belief is that this should be the hard part, but then you need to do, at some point you need to come up with solutions. Of course, you have the candidate solution, right? It's this the value for the control problem. So this is a start. So this is where you should start.
And just a very, very naive question: how do you relate your approach with some other approaches that people use in mean field optimal control or Mac-inverse control? There are some notions of viscosity solution with some partial results, existence or some class of test functions. So I guess you know this kind of thing. So how do you make a connection between your work and these ones?
Yeah. So okay. So the way I understand this. So now that there's lots of activity around this, so then maybe I'm missing some of the most recent results. But the way I see that there are essentially two ways to attack this problem. There is one way in which you adopt this lifting procedure. So you identify probability measures with random variable on some L2 space. And then so the big advantage of doing this is that you end up working in a Hilbert space, and there the theory is much better. But of course, the drawback of doing this is that, okay, there is some lack of, how should I say, universality in the choice of this lift. And then the equation is not so easily interpretable. So for instance, this equation, just to mention, this equation here, if I were to write with this lifting approach, so here, as you said, is Hamilton-Jacobi, so it's first order. But if I were to use this lifting technology, this is second order, or at least something that looks a bit like second order. So we are really far from this extrinsic viewpoint. We are really at intrinsic. So we really work in the space of probability measure. In fact, so to define these objects, we don't need to. Well, actually, we don't define them, first of all, because we work with upper and lower bounds, and we don't need to resort to this Lyon's derivative construction. So we really stay in the. So in this respect, we are in the intrinsical stream of research. Then I know that there are many results, for instance, by Gangbo, where it is with Hamilton-Jacobi equation, but somehow those results are, I would say, essentially inapplicable in our setting because so typically you need to have. So, okay, first of all, the form of the equation that they look at in those papers is mostly something that looks a bit like, instead of this term, you have some function of mu. This is probably the prototype of equation that they look at. And essentially, if you work with a displacement convex functional, which is not at all Lipschitz, by no means, then you violate all the assumptions that they have there. So our setting so our motivation was really to go away from any Lipschitzianity in the energy term, and profit from all the geometric structure of displacement convex functional. So gradient flows and functional inequalities and all these kind of things. So in this respect, I would say that the specialty of the method and the equation that we're looking at is really in the fact that we are able to deal under a certain specific structure with unbounded terms. And so we only need some kind of convexity, geometric convexity assumption. And this is what makes the difference between, I would say, the equations we look at and the equations that have been looked at, for instance, by Gangbo and co-authors.
Mm-hmm. Okay, just very few questions about the Schrödinger problem. The first one is that when you write down the FBSD system, in fact, this is very close to what people do in mean-field games somehow.
Yes.
Did you have a look at the connection with mean-field games of planning, which is very, very close to what you are doing, and what your results could say, or conversely, well, any connection is interesting to me.
Yeah, yes, of course, it looks pretty much like planning mean-field games, and of course, yeah, this looks like pretty much like the probabilistic representation of mean-field PDA systems. Actually, we looked a bit into this, and I mean, at the formal level, at least, if you look at those mean-field games that are variational, so that can be written as control problems, these are more or less the same objects.
Mm-hmm.
But somehow the difference is in the type of coupling terms. Maybe I will explain this. Okay. So if I try to do a very brutal reduction. So to me, the systems that are typically studied in mean-field games, if I rewrite them as Mekin-Vlasov control problems, they relate pretty much. But okay, you will tell me if I am wrong. To problems like this.
Yeah, this one, or you could require that at the terminal time, which is exactly what you do. Exactly. So
this is planning mean-field game, right?
Yeah, exactly.
So I think that the difference between this and as I said, the Schrödinger problems, because there are many ones that I didn't talk about today, but for instance, the one with lattice gases that Thierry mentioned, is a bit in the structure of the problem. So here, the mean field part comes through the cost. So it comes through the running cost. In the mean field Schrödinger and its brothers and sisters, the mean field part comes from the dynamics. So you typically have, so for instance, in our setting, it would be this thing. So of course you could do a change in variable and try to plug this into the cost. But then the thing that you get is not really does not really have a nice interpretation. And this has the effect that when you write down the coupled HJB Fokker-Planck system, you see the same structural difference popping up in the equations. So for instance, in the coupled HJB Fokker-Planck systems, we also have a nonlinearity in the Fokker-Planck that comes from this guy. And that's why I don't see how to directly import the methods to solve those systems to our systems unless you make some not really realistic assumptions on W. Yeah, that's so that's how they relate. They are both mean field control problems. In one case, the mean field part is in the dynamics. So Schrodinger problems are always something like you take a nonlinear dynamics, you allow for a correction, and you pay for the correction. This is more or less always the structure that you end up.
But just one comment is that in mean field game, you could have an interaction in the dynamics as well. So this is absolutely possible to put a mean field interaction. You can put any kind of dynamics. And then you can play as much as you want with the model. But I agree with what you say. Maybe we can carry on this discussion.
Maybe just to complement also vice versa, if you wanted to get a term like this one naturally in the context of the mean field Schrodinger problem, what you would do, you can do this Feynman cut penalizations of the probability measure associated to the n particle systems. When you do the large deviations, then you will pick up this term. So yes. So yeah, of course there is a lot of exchange. But okay, there is the obvious difference that our problem is born as a control problem, and the mean field games are born as fixed points of control problem. So there's this.
Yeah, absolutely, but we know how to pass from one to the other.
At the end, when you look at the equation, there more.
Okay, I think this is enough for me. So once again, congratulations,
Thank you,
Giovanni. So now we have to meet between the people of the committee. Thierry, can you confirm that there is another Zoom link for this?
Yes, I sent to all the people in the committee the Zoom link previously, so we can join there, and then we'll meet back Giovanni in I don't know sometime on this YouTube.
What I do suggest is that we have a 5-minute break so that we can have a bit of
perfect. I open the Zoom link, and if you can't access, let me know.
So we can be back on Zoom at 3:15. So maybe between 3:15 and 3:20.
Okay.
3:20 at the latest, because then we have plenty of things to do. We have to write down the report. Okay.
Okay.
Yeah, thank you very much for coming today. Goodbye.
See you later. Bye-bye.
On est désolé. Hein.
Hello, so welcome back.
No. We're waiting for François.
You have time to grab your hair. Tu peux te recoiffer maintenant.
C'est filmé, c'est sur YouTube en plus, fais attention. Ah voilà.
Non, mais je vais tout effacer.
Photoshop, il va se recoiffer.
Un tableau vert, c'est un tableau blanc, mais ça peut pas marcher.
Sur Zoom, il y a des filtres
pour les cheveux.
Non, mais pour, je sais pas, là. Ça a l'air plus...
Je voudrais dire juste que c'est pas par manque de respect, mais aussitôt que je peux, je vais partir parce que je suis en retard pour une autre réunion. Donc, je serai là juste pour ce qu'il faut.
Merci beaucoup. On va juste lire le rapport et puis après.
D'accord, et après je pars, Giovanni, désolé.
Oui, aucun problème.
Bon, tout le monde est là. William aussi. Okay. So, this will be in French. Giovanni, le jury a délibéré et je vais rendre compte du rapport. Tu as donné à distance un exposé très clair, de très grande qualité, qui a été apprécié par tous les membres du jury sur tes travaux, sur le problème de Schrödinger, transport optimal, contrôle optimal champ moyen, inégalité fonctionnelle. Tes travaux sont à l'intersection de différents domaines des mathématiques et cela couvre un spectre qui est large, qui va du calcul des variations au transport optimal, aux probabilités, en passant par les inégalités fonctionnelles. Et à cet égard, je dois dire que le jury est impressionné par la diversité des résultats que tu as obtenus, ainsi que par ta capacité à proposer différentes approches d'un même problème en utilisant des outils de géométrie, d'analyse ou de probabilité. Et ceci est remarquable. Et ton exposé a su rendre compte de la profondeur de l'ensemble de tes contributions. Et dans le rapport, le jury a voulu souligner les points suivants. La compréhension que tu as obtenue du problème de Schrödinger, que ce soit sous sa forme d'origine ou en présence d'une interaction champ moyen, et l'interprétation que tu as donnée à l'aide d'une loi de Newton sur l'espace de Wasserstein. Dans ce cadre, donc le problème de Schrödinger, tu as aussi obtenu des résultats fins sur le comportement en temps petit du coût anthropique ainsi que sur l'apparition d'un phénomène de Thorne-Pike. Tu as également d'autres résultats inspirés par le problème de Schrödinger, dont ceux sur les solutions de viscosité pour des équations d'Hamilton-Jacobi sur l'espace de Wasserstein, mais en fait également sur des espaces plus généraux. Et enfin, le jury a également beaucoup apprécié les résultats que tu as obtenus sur les inégalités fonctionnelles, à commencer par les inégalités de Sobolev logarithmiques modifiées pour des chaînes de Markov en utilisant des critères de courbure et des méthodes de couplage. À l'arrivée, je dois dire que nous sommes tous impressionnés par la maturité dont tu fais preuve maintenant, la maturité à un niveau senior dont tu fais preuve maintenant et dont tu as témoigné au cours de la présentation. Et les réponses aux questions que tu as eues vont dans ce sens et témoignent d'une profonde maîtrise du sujet. Je pense que le jury a souligné au cours des discussions l'excellence, la pertinence de ton activité scientifique sur des thématiques qui sont brûlantes, et ça c'est important. Et tu as clairement toutes les qualités pour être un brillant professeur ou un brillant directeur de recherche dans la suite de ta carrière académique, et naturellement, cela va de soi. À l'unanimité, le jury te décerne l'habilitation à diriger des recherches. Voilà, un très grand bravo, Giovanni.
Thank you all very much.
Bravo.
Bravo.
Et merci d'être invité, c'était un plaisir. Au revoir.
Okay, thank you all for
Giovanni.
Thank you all for coming.
Bientôt.
Special thank to the referees who, of course, it was a lot of work for them. And I hope to have the chance to meet all of you sooner or later in person to say at least hello and maybe talk about something else. Okay, so thank you again for connecting.
A pleasure. Bye-bye.
It was a pleasure.
Congratulations.
Thanks a lot, Giovanni.
Bye-bye. Bye-bye. Thank you.
Bye.
Congratulations for your. Je dis en français maintenant. Bravo.
Je viens vous dire bonjour.
Ok, à tout de suite alors. Bye bye.